All right, so let's go back to the examples that we were looking at on Monday. And we're gonna work through these two examples. Ask to draw all the possible products and then give a mechanism for reaction one. So let's start at reaction two. We already said that for that molecule, there's only one allylic site. So somebody tell me where the first product, what the product would look like, or at least one of them.
The double bond will move down one. That makes sense.
Here?
Yes.
And you're gonna put the, where are you gonna put the bromine? You're right, I agree.
Sir, come on.
Is it gonna go above that double bond? The one, yeah.
Yeah, I agree with that. What about that's the resonance product. What about the main product? What's that gonna look like? What reaction are we studying again?
Is it rearrangement?
No, the reaction. What's the name of this reaction?
Oh, let's see.
Isn't this allylic bromination?
Oh, yes.
So where's the allylic site? The allylic site is right here. Am I right? We have it highlighted. I'm gonna change colors. It's a different day. That's the site that's the original site. So what is that product gonna look like? That's what I'm asking. Where's the bromine gonna go?
One of them goes on the site.
Yes. Right. So that product, those two products come from this radical. Right, and that radical can do resonance. To give you a new radical that looks like that. So that's where the two products are going to come from. All right. All right, let's do the next one. How many products do you predict for that? In reaction one, that structure in reaction one, how many products do you predict? And how do you know, how can you say definitively how many products you're going to get?
It's 2 times the number of allylic sites.
2 times the number of allylic sites. And on Monday, we identified them, right? We got 2 sites. So we're expecting 4 products. And then we also talked on Monday about how some products are going to be formed faster than others, and some are going to be more stable than others. So let's go through the mechanism and see if we can answer those questions for this. All right, we're not going to go through the initiation step because I don't want to run out of room. But we know in the initiation step, what happens? For this reaction, what happens in initiation?
The radicals form. A reaction radicals.
Yeah, good, reactive radical. So we get a bromine, a reactive bromine radical, right? And then in the propagation step, we got an allylic site here. And one of these hydrogens here. Which one do y'all want to start with? It's up to you.
The main site. The
So
one
the
that's-
tertiary site.
Yes.
All right, let's do that. What's that? What's the process called here? When I'm taking off a hydrogen radical, I'm removing a hydrogen radical. What's that process called? Anybody? It has a name. And
Is it deprotonation?
not when you're removing a radical. Deprotonation is when you're taking off H plus. When you're taking off a radical, it's abstraction.
Abstraction?
Yes.
Oh.
Right. And it happens, I can't stress this enough, it happens the same way. You break the CH bond homolytically, you leave an electron on carbon, one leaves with hydrogen, and that hydrogen uses that electron to make a bond with bromine, right? So you get this radical here plus HBr. HBr is a side product. It does not participate. And I'm saying that because in the time that I've taught this class, 17 years, every time I put a question like this on the exam, somebody tries to use HBr as either a bromine source or in one of the propagation steps. It does not do that, right? The only thing that's going to react is going to be a radical. Once you make HBr, it's done, right? You can evolve it as a gas from the reaction. So that's that. And then what about the second site? I'm gonna have to draw it out. Same thing is going to happen here.
You're gonna break the double bond?
Not yet.
No.
We got to do abstraction again, just like we abstracted over here. All that's in propagation. You don't touch the double bond until you get ready to do your rearrangement, your resonance. So this is coming the same way, homolytic cleavage, and then bromine is going to pick up that hydrogen. So we're going to get HBr. And then a radical right there. Now, at this point, left the R off. At this point, you should be able to draw the resonance form. What does the resonance form for this look like? Right, here's your pattern, your allylic radical. How do you rearrange that? We've seen this already now. This is not brand new.
You draw the double bond in a near where you have the 2 CH2 group. It's not tertiary. What do you call that?
That's right.
Oh, okay.
So we want to do this, right? That's how that's going to happen. The the flow of electrons to do resonance on an allylic radical, it doesn't change, right? So you end up here with that radical. Anybody not see that? Because everybody is like Monday, it was like a mausoleum, and today is like a morgue. Anybody not see that or not understand like the arrows or whatever?
Yeah, it's the arrows for me.
Okay,
I don't get it.
so let me go back. And so when you have, first of all, in order to do resonance, you got to have a specific scenario. You got to have a donor and an acceptor adjacent. So for resonance, you got really three scenarios. You have a allylic anion, an allylic cation, or an allylic radical. All of them do resonance differently. For the anion, I'm going to move this pair of electrons here, and I'm going to write that in. Now I move this pair of electrons in the double bond here. Right, what that does is put the negative charge here. That's the whole purpose of doing resonance, is to spread the charge out over multiple atoms. And then put the double bond here, right? It was here, now it's on the other side. So that's the way you're able to share those electrons over all three atoms and delocalize the charge, make it more stable. With the cation, it's the same, right? You're going to shift the pi bond over. Notice the arrows though, right? I have a double-headed arrow, which means I'm moving 2 electrons, right? Let's go back even further than that. Every bond, whether it's a pi bond or a sigma bond, is made up of 2 electrons. Like that's fundamentally always going to be the case. So when I'm pushing arrows, I'm either going to use an arrow that's going to indicate me moving 2 electrons or 1 electron. Right. So here I move the pi bond over for the cation, and then I end up with the plus charge now being here on this carbon, and the pi bond moved over. You can see that. With the radical, it's different because you're only moving 1 electron. So the pi bond itself is composed of 2 electrons in overlapping unhybridized p orbitals, right? So I'm going to take one of these electrons and move it here, and take the other one and move it here onto the terminal carbon. And then this electron is coming here. So what that's saying is that I'm putting a pi bond, I'm moving the pi bond to here. So in the resonance form, that's what you're going to see. Right, the pi bond got shifted. And then now the single electron or radical is here versus here. Right, but all these follow the same pattern. Donor and acceptor, these are all allylic systems. Right, you have a donor and acceptor in the same, adjacent to one another. So for the anion, this is the donor, the pi bond is the acceptor. For the cation, this is the donor, this is the acceptor. For the radical, this is the donor, pi bond is the acceptor. And you can interconvert between those resonance forms. So when we have a radical like this, it's following this, it's in that pattern, it's an allylic radical. So when I rearrange it, and this is the resonance form for the top structure, I can always go back, right? That's why I use this double-headed arrow, meaning I can interconvert between those resonance forms. Same thing here. All right, so who was that said they didn't get the arrows?
It was me, Asia.
All right, jump in right here. What am I gonna do to rearrange this? And again, we have to think about why resonance is happening, right? Anytime you have charge, unpaired electrons, radicals, the goal is to take those things, either the charge or the unpaired electrons, and share them with other atoms that are nearby, either by doing a reaction or through resonance, because localized electron density, localized charge is bad, right? It's unstable. It destabilizes molecules. So having that radical sitting there on that carbon is not good, because that carbon does not want to be, it doesn't want to have that unpaired electron on it. So it wants to be able to share that. And the way you're able to share it is through, in this case, being in an allylic system and overlapping orbitals and then sharing electrons that way. All right, so Asia, what are we going to do here? How are we going to share that electron across the system?
When the double bond be moved to that carbon and well, yeah, the double bond would be take the place of the radical on that carbon.
Okay. Now
And the
we're gonna show
radical.
that. You're right. I agree with you 1000%. How are we going to show it? What am I, in other words, what are my arrows going to look like?
It's gonna be coming from the double bond to the carbon.
Like that?
Yeah.
And I'm gonna put the other electron here.
Yes.
Notice I'm putting it on the line. That matters. I'm not moving it to the carbon on the end. I'm putting it on the bond between this carbon and this carbon, right? Because what I'm trying to indicate is that I'm making a pi bond there. So I put the arrows in them on the line and not on any atom. And then here, I'm gonna take this electron and put it here on the atom, right? Not between a line or somewhere else, because where my arrow starts and stops matters, right? So my resonance form is gonna look like this, where the double bond is now here, the radical is here. And like that. That's what that set of arrows is gonna give me. Right, that set of resonance arrows is going to lead me to this structure right here. And when I'm doing radicals, it's always a fissure. It's never a double-sided arrow. That's another thing that's I've seen a lot of. I see it every semester, every time I teach the class. But radicals, you have to use single-headed arrows to move one electron, and you use a double-headed arrow to move 2 electrons. All right, so now let's do the questions about that. Now we can do, what's the next step in the mechanism? Anybody?
Are we on termination now?
We are. Add a page, sorry. We are on termination. That's the final step in any radical chain reaction. So we have this radical. We have this radical. And then we have this radical. I'm just not writing in the CH2s, and this radical. Right, and each one of these radicals is going to terminate with a bromine. right? What are the arrows going to look like here? How do I show those coming together?
The one-sided arrows are gonna meet in the middle.
Okay, good. So that's going to give me this product. Sorry. Right. And then we'll have that product from this reaction right here. Right. And then down here, same thing. I'm just like so. All right. So those are my 4 products. Here's the question. Which is more stable or the most stable? So which product? And which one forms the fastest? How do we know? Because we should know at this point. I talked about it Monday, and it was also in the video that was sent out, and it's in the book in the section on Allylic Bromination.
The
So between
amount of
those
time-
3 things, we should be able to answer that. Go ahead.
I just said the amount of times it's substituted.
Okay. So you mean when you say it, what do you mean? The radical?
Yes.
Okay. So which one of these radicals is the most substituted on this side? I mean, you have this one right here, which is tertiary. And then this is secondary. This is primary. I'm trying to do that. And this is also secondary. So which one is going to be the fastest? Let's start there. All right. The fastest radical is the one that's the easiest to get to. Let's think about it that way. So which one is the most accessible?
Would it be the primary one?
Yes. It is this one. So this is going to be the fastest form. Because that primary radical is more accessible. All right. What about, so which one do you think is going to be the slowest?
The tertiary.
Good. Tertiary. That's right. And that rate is going to be based on sterics, right? It's going to be based on how accessible that radical is, how much bulk is around it. Okay, which one is the most stable? What do you think? We went over this Monday at the end in the class, I think. So it should still be fresh if you went back and looked at it or refreshed yourself. How do we know about the stability? What do we base that on?
Is it still the carb? It's not carbocation. It's not based on it. No. Is it the opposite of the carbocation one?
No. And here in this case, Stability is going to be based on what the double bond looks like. So is the double, I need to rewrite that. Is the double bond more or less substituted? That's the question. Right, so each one of these double bonds has a certain substitution pattern. All right, so let me go back up here and refresh us. So we have unsubstituted, which is all hydrogens, monosubstituted, which has one carbon, disubstituted has two carbons, trisubstituted has three, and then tetra has four. So if we look at these, actually, you know what? I'm just gonna cut that or copy it. Paste it right here. So we look at these alkenes that are here. Which one of those is monosubstituted? Meaning the double bond itself only has one carbon attached to it.
The first one and the last.
This one.
No, wait, this last one, I
It's
think.
this one.
Yes.
Mono substituted. What about the first one and the third one? What's the pattern there? How many carbons are attached?
Die?
Yes,
Substituted?
not substituted. So it's got a carbon here. This one has a carbon here and here. So both of those are disubstituted. Right? What about the second one? It's got three carbons attached to it.
Substitute.
It's trisubstituted. So when we think about the stability of that alkene, the more substituted it is, the more stable it is, right? So the trisubstituted product is going to be the most stable. Right? All those, when you think about the stability of an alkene, it's similar. You think about it in a similar way of thinking about a carbocation, right? You have an alkene that has, let's say, tetrasubstituted. Each carbon in that alkene is sp2 hybridized, right? And then it's connected to these carbons here, which are sp3 hybridized. And so the electrons in the bond between the two carbons, the dipole is going this way towards that carbon. And that's a stabilizing effect. So those sp3 carbons donate electron density. That has a stabilizing effect on it. That's why the more substituted an alkene is, the more stable it is, because those carbon bonds are polarized towards the sp2 carbon. Anybody remember from part one, the connection between hybridization state and electronegativity? I'll buy lunch on that one.
Is it an inverse relationship? The more stable, the less electronegative?
Look, go back. Right now, we're talking about electronegativity and hybridization state. So it's not necessarily a question about stability as much as it is a question about what's the trend, right? Because remember, you have sp3, sp2, and sp hybridized carbons. Is that right? Y'all remember that from part 1?
Yeah.
All right. So when you think about the sp3, that's 25% S, sp2, 33% S, and then sp is 50% S. So the relationship is electronegativity increases as the percent S character increases. So you have increasing electronegativity. The more S character that hybrid has, the more electronegative the atom is going to be. I know that's a way back playback from part 1, but it's a very important concept. All right. Let's any questions about the product so we know which one is the slowest, and the reason this is important. Yes, Danielle, good question. Yes. That's why to that question, that's why the dipoles go the way they go. Because remember, if a bond is polarized, the dipole is always going to go towards the more electronegative atom. So yes. Great question. All right. Anytime you have a polarized bond, you're going to have the dipole in the direction of the atom that's more electronegative. All right. Let's see if we got 10 minutes left. Let's see if we can work this last problem here. Let me see how many people we got. 15 people out of 30 people. That's a shame. Oh, hold up. I can't stop sharing. All right, I'm gonna do this. I'm gonna take half of you all. Everybody write this question down. It's just an Allylic bromination problem. You don't have to go through the mechanism. I just want you to draw out the radicals that you'll get in propagation and the products. So let me give you a jump start. Where are your allylic sites on this molecule?
One is
Mm.
at the
Sorry, I was just going to say the double bond in the CH3.
So here, is that what you meant? Is that what you meant?
Yes.
And then here, right? Keep in
Oh.
mind, whenever you see this term allylic, all it means is adjacent to an alkene. So wherever your double bond is, the sites to the left and to the right of it are the allylic sites. Right? I'm gonna make 3 rooms, and does that sound automatic? We got 15 people. All right. So you should get an invitation. I want y'all to work this out and come back in 7 minutes. Actually, 6 minutes. That way we'll have 3 minutes to share. All right. So you should have an invitation to a breakout room. Draw all the products. Draw the radicals and all the products. You still got 5 people in the main room. You need to join a breakout room.
And Dr. Russell, can you zoom out for a second?
Zoom
So
out.
I need. Thank you.
Mhm.